welcome you all to session 3 of the chapter Frames of Reference. In the last session, we have derived Galilean transformation equations. We had considered two inertial frame of reference. One is S and another one is S dash. S is at rest and S dash is moving with constant velocity. And we arrived at equations like this. X dash equal to X minus Vt, Y dash equal to Y, Z dash equal to Z, T dash equal to T. So these equations are called Galilean transformation equations. These equations are called Galilean transformation equations. After deriving these equations, we also proved that length is invariant in Galilean transformation. Of course, fundamental quantities like length, mass and time are all invariant in Galilean transformation. We also proved velocity is variant in Galilean transformation, means it must also have the Galilean transformation equations. So what are the Galilean transformation equations? What are Galilean transformation equations for velocity? Right, if I consider this, we already derived that u dash equal to u minus v, right? So u is the velocity of the particle with respect to frame S. U dash is the velocity of the particle with respect to frame S dash. V is the velocity of the frame S dash. We have derived it in the last session, right? So this is called as Galilean transformation equation for velocity if a particle is moving along positive x-axis. So this is the equation. This equation is called as Galilean transformation equation for velocity if a particle is moving with velocity u with respect to frame S and the velocity u dash with respect to frame S dash, and v is the velocity of the frame S dash. If it is so, then this equation is called as Galilean transformation equation for velocity, right? If I consider it for x, yes, you can write it as ux equal to ux dash equal to ux minus v. So it is not moving along y, so let me take it as like this now here, uy dash equal to uy and uz dash equal to uz, because the particle is not moving along y and z axis. As the particle is moving along only x axis, we get this equation. Means the velocity with respect to the second frame will be equal to velocity with respect to first frame minus velocity of the second frame, right? So this was the equation which we have derived in the last session. Okay, in this session we will be deriving invariance of Newton's laws under Galilean transformation. So under Galilean transformation, Newton's laws are invariant, right? If you change from one frame of reference to other frame of reference, Newton's law will not change. So that will be the derivation of this session, right? So invariance of Newton's laws under Galilean transformation. Now let us derive this now here. Okay, first of all, let me make it clear. Newton's laws means it is particularly Newton's second law. We know that F is equal to ma is a mathematical form of Newton's second law, which includes both Newton's first law as well as Newton's third law, right? Means if you prove F is equal to ma is invariant in all inertial frame of reference, then it's enough that Newton's laws are invariant under Galilean transformation. So today I will be proving F is equal to ma is invariant if you change from one frame of reference to another inertial frame of reference. Okay, let us derive this. Invariance of Newton's laws under Galilean transformation. Okay, let us consider two frames here, two inertial frames. So this is the first inertial frame which has the axis x, y and z, whose origin is O, and let me consider this is as frame S. Now let me consider another frame like this. So this is a frame, this is x dash, this is y dash, and this is z dash. This is the frame S dash, which is moving with the constant velocity. What is that now here? V. This is origin O, and let me take it as origin O dash, right? Okay. Now, let me write something about this diagram here, right? So, we had considered two inertial frame of reference. Consider two inertial frame of reference. Consider two inertial frame of reference, S and S dash, right? These two are inertial frame of references, S and S dash. Okay, two inertial frame of references, S and S dash, such that S is at rest and S dash is moving with constant velocity. S dash is moving with constant velocity v, right? S dash is moving with constant velocity v along positive x-axis. So it is moving along positive x-axis. We have already considered like this in the last derivation also, right? These are the two inertial frames. We know what is an inertial frame. It is a frame which is at rest or moving with constant velocity. Okay, I took two frames which is at rest once, and S dash is a frame which is moving with constant velocity v. Earlier, at a time t equal to 0, O coincided with O dash, right? X and X dash are in a single line. Y axis and Z axis are parallel to each other, right? At t equal to 0, O coincided with O dash. As time passes, this frame is moving with the constant velocity v, right? Okay, so let me take like this. It is at this position now here, right? Okay, that is what I have written here. Consider two inertial frame of references, S and S dash, such that S is at rest and S dash is moving with constant velocity v along positive x axis. Now, let me consider a particle here. And this particle is moving along positive x axis. Okay, let me consider the velocity of this particle is u with respect to frame S. Okay, if a person is seeing from this frame, what is the velocity of this particle? Let me call it as u, and u dash be the velocity of the particle with respect to frame, which what say S dash. Okay, let me write about this. Let u be velocity of the particle. I have considered this is a particle whose velocity is u. Let u be velocity of the particle with respect to S, and u dash be its velocity with respect to frame S dash. Okay, let u be the velocity of the particle with respect to frame S, and u dash be the velocity of the same particle with respect to frame S dash. Okay, now in order to prove, do you understand here what is the frame out of this derivation? In order to prove f is equal to ma is invariant and the Galilean transformation, first we need to prove A is invariant. First we will be proving acceleration is invariant, then I will be proving force is invariant, right? Okay, we came to know that velocity is variant. Considering that, let me continue with acceleration. Okay, so just I consider u be velocity of the particle with respect to frame S, this is the particle, and u dash be the velocity with respect to frame S dash. Now let me take a Galilean transformation equation for velocity. Okay, let me continue. So I am proving Newton's law is invariant under Galilean transformation. Okay, now let us consider using Galilean transformation equation for what we say here, velocity. We know what is the relationship between u and u dash. If it is moving along positive x-axis, what is the relation we have already derived in the last class, right? So what is the relation between u and u dash? As u is the velocity with respect to frame S, and u dash is the velocity of a particle with respect to frame S dash. So what is the Galilean transformation equation for velocity? Okay, we know the Galilean transformation equation for velocity is u dash is equal to u minus v, right? Okay, we got Galilean transformation equation for velocity, that is u dash equal to u minus v now here. Next, I need acceleration, right? First of all, I need to prove that acceleration is invariant. That's why I need acceleration, right? In order to get acceleration, we know that what is acceleration? Change in velocity divided by time taken, dv divided by dt. Means if you differentiate velocity, you get acceleration, right? So do remember, the differentiation of velocity is always acceleration. That is the reason we already got the velocity. Let me differentiate to get acceleration. Before that, let a be the acceleration of this particle, right? Let a be the acceleration of this particle with respect to frame s, and a dash be the acceleration of the particle with respect to frame s dash. Okay, if a person is standing at this frame s and he is observing this particle, he feels that what is the acceleration of this particle? Let me take it as a, and a dash be the acceleration of the same particle with respect to the frame s dash. Okay, till here we have arrived here. Next, what to do? Let me differentiate it. Right, we know whenever we differentiate velocity, we get acceleration. So what shall I do now here? I will be differentiating. See, let me differentiating with respect to time t. Okay, with respect to time t, let me differentiate it. So what do I get now here? du dash divided by dt is equal to d by dt u minus what we say here? V. Shall I tell like this? Du dash divided by dt. Okay, this is differentiation of velocity. What do you get now here? A dash, right? Okay, now that is equal to, what is the differentiation of, okay, before I write it, okay, let me simplify this. U minus e. What is differentiation of u? Du divided by dt minus, what is differentiation of v with respect to t? Okay, as this velocity is constant, it is not changing with respect to time, means differentiation of v with respect to time is what now here? 0, because it is not changing, because this frame is moving with constant velocity, then only it is inertial, right? So that is why we get dv by dt is nothing but 0. So we will be arriving at du divided by dt itself. What is du by dt? That is nothing but acceleration. Okay, what is this side? A dash. Since a dash is equal to a, means these two are equal, shall I say like this? Acceleration is invariant under Galilean transformation. Okay, we have proved that acceleration is invariant under Galilean transformation. Under Galilean transformation, right? I have already told you, to prove f is equal to ma is invariant, first we need to prove a is invariant, right? Simple. So we have proved that acceleration is invariant under Galilean transformation. How did I prove? I took Galilean transformation equation for velocity. I differentiated it with respect to time t. If I differentiate, I will be getting it as du by dt minus 0. Why 0? Because this velocity is not changing with respect to time. So dv by dt is 0 now here. What do you get? Du by dt, that is a dash equal to a, means acceleration is invariant under Galilean transformation equation, right? Okay, if the question is asked like this, show that acceleration is invariant under Galilean transformation, till here we need to write, right? But the question is, show that Newton's laws are invariant. So whenever to prove Newton's laws are invariant, first we need to prove acceleration is invariant. So first of all, we need to write a dash equal to a, then I will be continuing and I will be proving f is equal to ma is invariant. Okay, that is force is invariant. Okay, let me continue. Okay, after we came to know that acceleration is invariant, that is a dash equal to a, let me take force now here, right? Now let me check it out. Is force variant or invariant? Okay, let me write about this line. Let F be force acting on the particle. Okay, on this particle, let F be force acting on the particle of mass, what we say here, m, right? What is the mass of this particle? Let me take m, because I want Newton's second law, F is equal to ma. So let me take the mass of the particle be m. Okay, come on. Tell me, is m variant or invariant? I already told you, in Galilean transformation, basic physical quantities like length, mass, time are invariant, right? So let F be force acting on the particle of mass m with respect to frame. With respect to frame, what shall I take now here? With respect to frame, yes. What is the force acting on this particle? Let me take it as F. And F dash be force acting on the same particle. Force acting on the same particle with respect to frame. What we say here? S dash. Right? So, as mass is same, I have not changed force. Okay, let me check it out. Let F be force acting on the particle with respect to frame, yes. And F dash be force acting on the particle with respect to frame. What we say here? Yes dash. Now, we have arrived at A dash equal to A. Let me tell you, as we know that as mass is invariant, we know that mass is invariant under Galilean transformation. As mass is invariant, mass is not going to change now, right? So as mass is invariant, multiply m on both sides. Since it is invariant, I will be multiplying m on both sides of this equation. What do I get if I multiply m? M into A dash equal to m into A. Why did I multiply m on both sides? Because m is invariant. We know that length, mass and time are invariant under Galilean transformation. So I will be multiplying m on both sides. Okay. Now, if you multiply m on both sides, what did you get here? M A dash. Shall I write instead of m A dash? F dash. Yes. That is equal to, what is m A? That is nothing but F. Right. Again, we came to know that F dash equal to F. Okay, what does it indicate? Force is also invariant. Do you understand? Let me conclude that force is invariant under Galilean transformation. Galilean transformation. Force is invariant under Galilean transformation. If force is invariant under Galilean transformation, of course, Newton's laws are invariant under Galilean transformation. So, I will be concluding this by the statement. Hence, Newton's laws are invariant under Galilean transformation. Under Galilean transformations. Okay, same. Force is invariant under Galilean transformation. It indicates that Newton's laws are also invariant under Galilean transformation. Okay, this is the question which can be asked. Okay, right? Okay. If the question is asked, show that Newton's laws are invariant under Galilean transformation, what you need to show? You need to prove that F is invariant. F is equal to ma, same now here, right? F is invariant under Galilean transformation. To prove F is invariant, first we need to prove acceleration is invariant. So first we need to prove A is equal to A dash, then multiplying m on both sides because m is invariant. So we will be getting with F is equal to F dash. It shows that F is invariant, thus Newton's laws are also invariant under Galilean transformation. So this is the derivation, right? So we proved that Newton's laws are invariant under Galilean transformation, right? Okay. Next, we will be proving law of conservation of momentum. Okay, we will be considering one situation and let us prove that law of conservation of momentum is also invariant under Galilean transformation. Now, let us begin with this derivation. So, let me tell you its frame out now here, right? So, we are proving law of conservation of momentum. So, first we need to understand what is law of conservation of momentum, right? If I take two masses here, right? If I am taking mass m1 and mass m2, so let me take a situation like this: before collision and after collision. Okay, let me explain this law by using this concept. Right, if m1 is moving with velocity u1 and m2 is moving with velocity u2, right? So they collide and again they move, right? Before collision, the velocity of m1 is u1 and velocity of m2 is u2. After collision, velocity changes. It moves with velocity v1 and m2 moves with velocity v2 here. Let us consider like this: m2 is moving slow, m1 is moving fast, right? They collide and again they move. After collision, the velocity changes. Let me take before collision, the velocity of m1 is u1 and velocity of m2 is u2 before collision, right? After collision, velocity changes to v1 and v2 for m2 now here, right? Okay. So according to law of conservation of momentum, total momentum before collision, before collision is equal to total momentum after collision, right? So total momentum always remains the same, right? Before collision is equal to total momentum after collision. Okay, what is total momentum before collision? What is momentum? Mass into velocity. Okay, total momentum before collision, m1 u1 plus m2 u2, right? Momentum of this plus momentum of this, that is total momentum. Total momentum before collision is equal to total momentum after collision, m1 v1 plus m2 v2, right? So this is called as law of conservation of linear momentum, or simply law of conservation of momentum, right? Okay, so do remember, law of conservation of momentum means total momentum always remains same, right? If I consider in terms of collision, total momentum before collision is equal to total momentum after collision, and here we will be proving this law holds good in any inertial frame of reference. If you change from one inertial frame of reference to other uniform frame of reference, the law will not going to change and it remains same. That is what we are proving now, that is invariance of law of conservation of momentum under Galilean transformation. Okay, let me prove this. Let me begin with the derivation. Prove that law of conservation of momentum is invariant under Galilean transformation. Okay, let me take. Okay, as usual, we will be taking two inertial frame of references. Okay, first of all, let me take this is coordinates x, y, and let me take this coordinate as z, and the origin is O and the frame is S, right? This is what we usually took now here, right, to derive. Okay, let me consider another one now here. So this is a frame now here of coordinates x dash, y dash, and z dash, such that x and x dash are in a single line, y is parallel to y dash and z is parallel to z dash, and its origin is O dash. At a time t equal to 0, O coincides with O dash. As time passes, this frame will move here, right? Okay, see. So this frame is a moving frame, and this is the frame which is at rest. This frame is moving with constant velocity v. Okay, let me call this frame as S dash, which moves with constant velocity v. Right? This is a rest frame and this is a moving frame. As it moves, there will be a certain point where O coincides with O dash. That time, let me take t equal to 0, right? And when it passes, again, let me consider at time t now here, this is at this position, and it is moving with velocity v with respect to frame S now here, right? So there are two frames of reference. Okay, let me begin with the derivation. Okay, as usual, let me write about this now here. Consider what we need to consider: two inertial frame of references. Inertial frame of references. Consider two inertial frame of references, which are those S and S dash, such that S is at rest, and S dash is moving with what we say here, velocity. Which velocity? Constant velocity. Let me write it like that. Moving with constant velocity. Okay, S dash is moving with constant velocity v along positive x-axis. Let me take along positive x-axis. This is the same introduction which I had given to the earlier derivation also. Okay, the derivation begins like this. Okay, what I need to prove now? Here I need to prove law of conservation of momentum. Right. So I will be taking a collision case, and let me prove it now. Right. Okay. Let me take before collision and after collision concept. Before collision, let me take like this. That is after collision. Okay, just I have introduced what are these now, right? Now, before I continue with the derivation, let me take here, right? One is before collision. Let me consider like this. This is a frame x dash. Let me take it as after collision. Let me consider like this: before collision, after collision. Okay. Now I need to take two particles, right? Let me consider this is a particle, right, of mass m1, it is moving in this direction. Let me consider unknown particle of mass m2 which is moving in this direction. That is before collision. After collision, m1 will be moving in this direction. Okay, let me take like this. Particle, let me take like this, m1 which is moving in this direction, m2 which is moving in this direction. As I have already told you, to prove law of conservation of momentum, let me take this collision case. Total momentum before collision is equal to total momentum after collision. Come on, tell me. Let me take its velocity in here, right? Okay. What is the velocity of m1 with respect to frame s? Let me take it as u1. Okay. Let velocity be u1. And what is the velocity of this here? Let me take it as u2. Okay. Velocity is u1 and u2. This is what here? With respect to frame. What we say here? Yes. Do you remember? I am taking velocity with respect to frame. Yes. Okay. Now, what is the velocity after collision? Let me take it as v1 is the velocity of m1, v2 as the velocity of m2. That is again with respect to frame s itself. First of all, I speak with respect to frame s. Then I will be moving on to the with respect to frame s dash. With respect to frame s, this is the velocity u1. Its velocity is u2. That too before collision. Right? After collision, velocity changes. Let me take v1 and v2 be the velocity of this particle with respect to frame s. Okay. Let me write about this. Okay. Let, what is that now? Let u1 and u2 be velocities of particles of masses m1 and m2. Okay, see, let me consider. Let u1 and u2, what are those? These are the velocities of the particles m1 of mass, velocity of particles of masses m1 and m2, that is with respect to frame s before collision. Okay, do you understand? This is before collision concept. Okay, let u1 and u2 velocities of the particles of masses, velocities of masses m1 and m2, the two before collision. And do you remember it is with respect to frame s. And v1 and v2 be velocities of masses m1 and m2. Okay, let v1 and v2 be the velocities of masses m1 and m2. That too what now here? After collision. Do remember this is again with respect to frame. What shall I say now here? Yes. Okay, I am speaking with respect to frame yes. If the observer is seeing from this frame, the velocity of m1 is u1, velocity is m2 before collision, and after collision its velocity is v1, its velocity is v2. Just I have written here, right? Okay. Let u1 and u2 be velocities of particles of masses m1 and m2 before collision, right? That too with respect to frame s, and v1 and v2 velocity of masses m1 and m2 after collision, that is with respect to frame yes. Now, what shall I apply? Shall I apply law of conservation of momentum? Okay, let me write like this. According to law of what we say here? Conservation. Law of conservation of momentum. Okay, according to law of conservation of momentum. Okay, what is law of conservation of momentum? Total momentum, we know that total momentum before collision, see here, total momentum before collision is equal to total momentum, what we say here, after collision. Okay, see here. Total momentum before collision is equal to total momentum after collision. I am speaking with respect to frame s, right? Okay, what is total momentum before collision? m1 u1 plus m2 u2. Shall I take like this? m1 u1 plus m2 u2. That is equal to total momentum after collision m1 v1 plus m2 v2. m1 v1 plus m2 v2. Let me take it as equation number 1. Okay, see, what is equation number 1? Equation number 1 is The law of conservation of momentum with respect to frame, yes. Okay, do you understand? With respect to frame, yes. What is the law of conservation of momentum? m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. That is equation number 1. Okay. Now, I need to solve this. That is the reason. Let me take what are the velocities at this position. Let me take this equation here, right? So that I will be considering it for further cases. m2 u2 that is equal to m1 v1 plus m2 v2. This is equation number 1. Okay. So this is what I arrived at. Okay. Let me take this equation here. I arrived at this equation. This equation gives law of conservation of momentum with respect to frame. Yes. Now what I will be doing? I will be taking with respect to frame. Yes dash now here. Okay. Now continue with this now here. Now I will be considering with respect to frame yes dash. Now we know that with respect to frame yes dash, velocity will be changing. Let me take the velocity of m1 is u1 dash, velocity of m2 is u2 dash. This is with respect to frame yes dash. If I am saying with respect to this frame, what is the velocity of m1? u1 dash. What is m2? u2 dash. Right, again, what is its velocity now here? That is v1 dash and v2 dash be their final velocities after collision, right? Velocities with respect to, what is that now here? Yeah. Okay, let me take like this. So with this is after collision itself. So these are the velocities with respect to frame yes dash. This is also with respect to frame yes dash. Okay, now let me continue. Let me write about this. What are these u1 and u2 dash? Let me take. Let u1 dash and u2 dash be velocities of masses m1 and m2. Okay, that too before collision. Let me take like this. Before collision, that is with respect to what we say here, frame yes dash. Yes. With respect to frame yes dash, u1 dash is the velocity of mass m1 and u2 dash is the velocity of mass m2. Okay. So here, let u1 dash and u2 dash be velocities of masses m1 and m2 before collision, and v1 dash and v2 dash be velocities of masses m1 and m2, that to what we say here, after collision, right? This is after collision, that to with respect to which frame? With respect to frame yes dash. Okay, just I introduced about these velocities, right? Okay, let u1 dash and u2 dash be velocities of the masses m1 and m2 before collision, and u1 dash and v2 dash, that to after collision with respect to what we say here, yes dash. Now shall I use law of conservation of momentum as I have used here? Okay, let me write here. According to law of conservation of momentum. Okay, according to law of conservation of momentum, what does it says? Total momentum before collision is equal to total momentum after collision. I am considering about this frame yes dash. Okay, what is total momentum before collision? m1 u1 dash. Shall I say like this? m1 u1 dash plus m2 u2 dash, right? m2 u2 dash, that is equal to m1 v1 dash. Okay, m1 v1 dash plus m2 v2 dash, that is m2 v2 dash. So this is the law of conservation of momentum with respect to frame yes dash. Okay, let me simplify it now here, right? Okay, so we got this expression here. Okay, let me take mathematical expression, that is m1 u1 dash plus m2 u2 dash is equal to m1 v1 dash plus m2 v2 dash. Now I'll be using Galilean transformation equation. You know what is Galilean transformation equation in case of velocity, because velocity is variant. Okay, I'll be using Galilean transformation equation. Okay, let me write about this. Okay, the next is using Galilean transformation. Okay, I'll be using Galilean transformation equations for what we say here? Velocity. Right? We know that we have derived it. What is the Galilean transformation equations for velocity? Come on, tell me. What is the relationship between u1 dash and u1? By using Galilean transformation equation, we know that what is u1 dash? u1 dash is equal to u1 minus v, right? u1 dash equal to, what is the relation between these two? u1 dash equal to u1 minus the velocity of the frame s dash, right? That is, this is the relation that we already derived it, right? Okay, let me write about this two now, right? What is this? u2 dash equal to, what is the relation between u2 and u2 dash and u2 minus v. Okay, let me write about this Galilean transformation equations for these two velocities now here, right? Okay, that is v1 dash is equal to v1 minus v, right? Then v2 dash and v2 prime, that is equal to v2 minus v. Okay, what are these? These are Galilean transformation equations for velocities. We are combining these two now, right? So the equations which combine the physical quantities of two inertial frame of references, those are called as transformation equations. These two are Galilean transformation equations, that too for velocity, and we got with this. Now I will be substituting these all equations in this now here. Okay, now let me substitute all this in those equations now here, right? Okay, what do I get now? If I substitute it, what do I get now? Substituting. Okay, substitute here. In place of u1 dash, I will be substituting u1 minus v. Okay, what do I get now here? m1, what is u1 dash? u1 minus v plus m2, right? Here plus m2. What is u2 dash? u2 minus v, Galilean transformation equation for velocity. u2 minus v, that is equal to m1. What is v1 dash? v1 dash is v1 minus v, v1 minus v plus m2. What is the Galilean transformation for v2 dash? v2 minus v, v2 minus v. Now let me simplify it. What do I get? m1 u1, multiply this, minus m1 v plus m2 u2 minus m2 v, that is equal to, multiply this m1 v1, multiply this m1 v, right? So plus m2 v2 minus m2 into v, right? Okay, just to observe here also there is minus m1 v1, here, sorry, m1 v, there also minus m1 v. Shall I cancel it out? Yes. Then here also there is minus m2 v, here also there is minus m2 v. Let me cancel it out. What is remaining, right? We get with m1 u1 plus m2 u2. This is remaining. That is equal to m1 v1 plus m2 v2. Let me take it as equation 2 now here. Now I'll be comparing equation 1 and equation 2. Are they same? Yes, they are same. Means law of conservation of momentum is same for both the frame of reference. This I took in case of frame of reference S2. This is frame of reference S1. By using Galilean transform equation, I proved that these two equations are same, right? Shall I write like this? From equations 1 and 2, from equations 1 and 2, both are same, right? As equations 1 and 2 are same, law of, what we say here, conservation of momentum law of conservation of momentum is what we say here, invariant. Why invariant? Because they are same, right? If they are same, we call it as invariant. It is not going to change on you, right? The law of conservation of momentum is invariant under which transformation? Galilean transformation, right? As these two equations are same, that's why I have written like this from equations 1 and 2. Law of conservation of momentum is invariant under Galilean transformation. So this is the derivation, right? So in the examination, the question will be asked like this: show that law of conservation of momentum is invariant under Galilean transformation, and you need to derive like this, right? So first of all, we need to take two objects, two particles, mass m1 and m2. We will be taking before collision and after collision. I'll be using law of conservation of momentum. Total momentum before collision equal to total momentum after collision. First, I'll be considering it to frame S. I get equation number 1. For frame S2, I'll be getting one equation. I'll be using Galilean transformation equation and arriving at one equation which is similar to the equation number 1. As both the equations 1 and 2 are similar, I'll be concluding that law of conservation of momentum is invariant under Galilean transformation. So in this session, we have derived two derivations. One, Newton's laws are invariant under Galilean transformation. That is also 5-mark question. And another one derivation, that is law of conservation of momentum is invariant under Galilean transformation. Thank you.